Hey there, everybody. First things first, I apologize if you hear my children screaming in the background. They're always fighting about something I can't control, the noise they make, so I apologize in advance. We finished off the course by doing 3 sections of Chapter 6. Chapter 6 takes the idea of area under the curve, which we've talked about before, and it shows how integrals can be used to calculate other things, like area trapped between two curves, as we're going to talk about today. Integrals can also be used to calculate volumes, it turns out, and we'll do that in sections 6.2 and 6.3. So we end the course with some sort of geometric applications of integration. I should say that I was hoping to show you some more concrete applications of integration, but we're out of time. So in particular, this section 6.1 has some very nice applications in the social sciences, but again, we're out of time, so I can't show them to you. Okay, so the point of today is to talk about how you get the area trapped between two graphs. How do you do that? As opposed to the area under the curve, which is the area trapped between the graph of a function and the x-axis. So just by way of setup here, this left-hand picture here is what we've been thinking about for a while. So that left-hand picture, that is the integral from a to b f of x dx. Right, that'll give you that area there. What about this area here? You have now not a region trapped between the x-axis and a function, but a region trapped between two functions. How would you calculate that integral? Or sorry, that area. It turns out that area is also an integral. It's the integral from a to b. You take the top curve and you subtract off the bottom curve. It turns out. Okay, so if you want a justification of that, here's a couple of pictures to justify it. That region S here that we're thinking about, if you want to get that thing's area, you could approximate its area with rectangles just like we approximated this geometric area here with rectangles before. Same idea. Now the rectangles here, they go like above and below the x-axis, but that's fine. They still have a width at the base. They still have a height. Now the height, though, is given by the distance between the two curves. And the distance between the two curves is the top curve minus the bottom curve at a given point. So at this point right here, right, the distance from the top of this rectangle to the bottom is given by the top function minus the bottom function. So you have a width, a tiny width, delta x. You have a height given by the distance between the two functions, given by that difference there. Okay, so all that to say, all the stuff we've been doing translates exactly to this. If you're given two curves and want to know the area trapped between them, you can set up an integral where you just have top curve minus bottom curve. So I'm going to show you 3 examples here. And much of this is actually just practice with the geometry of like a visualization. So can you visualize what's happening here and then set up the appropriate integral? So actually for all 3 of these examples, it says find the area of the region. On your exam, it might say set up an integral or integrals, depending. But set up something that would find the area, and then you don't actually do the calculation. So in this one, I'm going to focus more on the setup and the visual than the calculation itself. Okay, so for this first one, we have to be able to visualize what region we are talking about. So to do that, let me draw both of these curves. So here's y equals x, like that. And then here is y equals x squared, like this. So the region we are talking about is this little slice right there. So we have to think about the area of that slice. Now it's important to be able to visualize this properly because you have to know, as this formula suggests up here, right? You have to know which curve is on top and which curve is on bottom. So here it's clear from the picture that in the region we're talking about here, in this blue region, y equals x is on top and y equals x squared is actually underneath that. So you might think that y equals x squared would be the top curve, and it is most of the time, but for this tiny little slice, it's actually not. Okay, so to set up this integral, we have to know where the region starts and where it ends. So like in this picture here, a is my start point of the interval and b is my end point. So we have to know what that point right there is and what that point right there is. So we have to figure out, and you can see it from the picture, right? But we have to figure out where y equals x and y equals x squared, where do they intersect? Where do they hit each other? And if you ever want to know where two curves intersect, I believe we've talked about this before, you set them equal to each other in C. So we get what? 0 is x squared minus x. So 0 is x minus 1. So x is 0 and 1. So you have to be a little careful at this step here. You are tempted perhaps to divide by x, but generally speaking, you shouldn't divide by variables because you could be dividing by 0 and throwing solutions out. So if you divided by 0 at this step, you would lose this solution here of x equals 0. Oh, wrong thing. You would lose that solution of x equals 0. Okay, so we know this is 0 and this is 1. So now to set up the integral, bring it over here, the area we care about is like this. The integral runs from 0 to 1. We have top curve minus bottom curve. And there you go. There's an integral that will give you the area of this little sort of orange slicey looking little thing here, right? Little crescent moon almost looking thing. Okay, so I want to keep this video fairly short, so I don't want to focus so much on the stuff we know already. We know how to calculate this integral. So if you had to calculate it, you could based on previous material. For this example, though, I will do it real quick, just as a reminder. So we get x squared over 2 minus x cubed over 3. That runs from 0 to 1. So this is now a half minus a third minus, plugging in 0 everywhere gives you a 0. So there's a minus 0 there at the end. So in the end, we learn that area is 1/6. And there you go. There's the answer. Okay, so again, the point of these examples today are more of a, can you visualize the region, and then can you set up an appropriate integral? So again, for the next two examples, I'm going to stop right here, because I assume you can calculate these integrals given what we did in the previous chapter. Okay, so let's move on. So now we want the region enclosed by a bunch of different curves. So let me sort of draw what's happening here. Okay, so x squared minus x minus 3. I don't know much about how that looks if I don't have a calculator maybe, but I do know that its y-intercept is -3. I also know it's a parabola that opens up. So it's something like this. I mean, who knows exactly, right? But so there's y equals x squared minus x minus 3. And then y equals 4x minus 7. Let's think about that. That's a line whose y-intercept is -7, so but its slope is 4, so it's building up. So it's something like this. And actually, let me draw its y-intercept much lower. So something like this. So here, this is, my scale is off, but that's all right. There's -7, there's -3. So again, we get kind of something that looks similar to the last one. I guess that's not surprising because the last one we also had a line slicing above a parabola, so same kind of idea. So let's think about these intersection points. Where is that? Where is that? Before we will process this x equals 3, but let's think about just what's enclosed by these two curves first. So again, we have to set these curves equal to each other and see what we get. So x squared minus x minus 3 is 4x minus 7. So let's rearrange this. We have x squared minus 5x plus 4. So if I factor that, I get x minus 1, x minus 4 is 0. So the intersection points are x equals 1 and x equals 4. So there's a 1. There's a 4. Okay, so if you just sort of blindly went ahead like we did last time, you would go from x equals 1 to x equals 4. However, now let's finally process this. We were told x equals 3 also, right, is what we want. So now I come in and I say, well, here's x equals 3. And actually, there's actually, sorry, a slight typo here. I meant to have comma x equals 1. Sorry. So you see, without that x equals 1, things are ambiguous, aren't they? Do you want to the left of x equals 3? Do you want to the right of x equals 3? So sorry, I meant to have the x equals 1 there so that we know it's to the left. So we're filling in like this. Again, not the green here, not this. We're going to ignore that. Whoop. Okay, so with all that ambiguity gone, we can now set up an integral like this. Integral from 1 to 3. We don't go all the way to 4 because we were told to stop at x equals 3. And now we have to do top curve minus bottom curve. Here is my top curve. Here's my bottom curve. I have to subtract off the entire thing. Dx. And there you go. So for this one, I will stop at this. If you want to calculate this on your own and check your answer, the answer is 10/3 off of this. So again, the important thing is to be able to visualize and then set up an integral. And I guess another important thing is for me to include all the information I meant to include, of course, right? So there's a lesson for me here also, I guess. Okay, so let's do the last one here. The region bounded by the curves x equals 0, y equals x, y equals x squared, and x equals 3. It appears that I remembered to include my other vertical x line on this one, so that's good. Okay, so we've already thought about y equals x and y equals x squared. So we just draw them again. So here's y equals x, like that. And actually, let me make it go through the origin for real. Y equals x is like this. And then y equals x squared is like this. Again, we already have this picture. So before, we went from x equals 0 to x equals 1 because it just said the region trapped by those curves. But now it says to go from x equals 0 to actually x equals 3. And let me actually flatten this out a little bit so it looks a little nicer. Oh, blue is fine, thank you. Okay, so let me move the 1 over a little bit. Sorry. Well, again, sorry. This is like watching your grandma try to use a web browser for the first time. There we go. Okay. So here's x equals 1. I'm going to butcher my scale. I'm going to put a 3 right there. And so now the area we care about is trapped there, but then there's also some area trapped over here. And then it stops at x equals 3. So the reason I'm showing you this example is to think about, so how do we deal with the fact that the blue curve is the bottom curve sometimes, but the top curve other times? How would you deal with that? And the answer is you just have to do 2 separate integrals. So here, the overall area is like this. It's the integral from 0 to 1, x minus x squared dx. That picks up the green area over here. And then you have to add to that the integral from 1 to 3, x squared minus x dx. Take into account that the x squared and x curves, they sort of swap places. So that second integral picks up that green area. So all that to say is sometimes if you have an area trapped between 2 curves, you might not get a single integral that handles that. You might need a couple or maybe even 3 or 4. I don't know. It depends on how often the top and bottom curves sort of switch roles. So if you want it also over here, right? So as I said, actually, my bad. I meant not x equals 0, but x equals -1 or something, right? Then you'd have to have another integral like this, -1 to 0, x squared minus x. You'd have to have that up front, plus those other guys. So again, the geometry dictates how many integrals you have and what the bounds on the integrals are. And again, just for the sake of time, I'm not going to evaluate these, but we already knew that this first one was 1/6. The second one, I can just tell you, is 14/3. So if you would like to check your answer, you can. The total area is 14/3 plus 1/6. And as you can tell from the picture, we're expecting way more area to be over here. Right? There's a much bigger chunk than this tiny little slice down here. And that's reflected in the answer. So 1/6, this 1/6 here, corresponds to that tiny little slice up front. And then this 14/3, which is way bigger than 1/6, corresponds to all that green that comes after crossing the x equals 1 threshold. Okay, so all that to say, this is what section 6.1 is. Given two curves, can you calculate the area trapped between them over a given viewing window? Now, the application I was going to show you, but we don't have time, is called the Gini index. This is in your textbook. So if you want to see a really nice application of this kind of thing, you can just read that on your own. The Gini index is a way of quantifying the level of income inequality in a country. So it's sort of a classic social science-y application of the sort of area trapped between two curves that you calculate with an integral. Okay, so in the next couple of sections, we'll actually use integration to calculate volumes for us, even though integrals are, of course, designed to calculate areas. So that's sort of a nice other last bit of geometric application.